étendue or étendue, etendue, French pronunciation, ady, is a property of light in an optical system, which characterizes how spread out the light is in area and angle. From the source point of view, it is the product of the area of the source and the solid angle that the system's entrance pupil subtends as seen from the source. Equivalently, from the system point of view, the étendue equals the area of the entrance pupil times the solid angle the source subtends as seen from the pupil. These definitions must be applied for infinitesimally small elements of area and solid angle, which must then be summed over both the source and the diaphragm as shown below. Étendue may be considered to be a volume in phase space. Étendue is important because it never decreases in any optical system where optical power is conserved. A perfect optical system produces an image with the same étendue as the source. The étendue is related to the Lagrange invariant and the optical invariant, which share the property of being constant in an ideal optical system. The radiance of an optical system is equal to the derivative of the radiant flux with respect to the étendue. The term étendue comes from the French étendue géométrique, meaning geometrical extent. Other names for this property are acceptance, throughput, light grasp, light gathering or collecting power, optical extent, geometric extent, and the AΩ product. Throughput and AΩ product are especially used in radiometry and radiative transfer where it is related to the view factor, or shape factor. It is a central concept in non-imaging optics. Definition: an infinitesimal surface element, ds, with normal ns is immersed in a medium of refractive index and the surface is crossed by, or emits, light confined to a solid angle, dω, at an angle θ with the normal ns. The area of ds projected in the direction of the light propagation is ds cos θ. The étendue of this light crossing ds is defined as dg equals n2 ds cos θ dω. Display style mathrm dg equals n2 mathrm ds cos θ mathrm dω. Closing curly bracket. Because angles, solid angles, and refractive indices are dimensionless quantities, étendue has units of area, given by ds. Conservation of étendue. As shown below, étendue is conserved as light travels through free space and at refractions or reflections. It is then also conserved as light travels through optical systems where it undergoes perfect reflections or refractions. However, if light was to hit, say, a diffuser, its solid angle would increase, increasing the étendue. Étendue can then remain constant or it can increase as light propagates through an optic, but it cannot decrease. This is a direct result of increasing entropy, which only can be reverted if a priori knowledge is used to reconstruct a phase-matched wavefront, such as with phase-conjugated mirrors. Conservation of étendue can be derived in different contexts, such as from optical first principles, from Hamiltonian optics, or from the second law of thermodynamics. In free space consider a light source sigma, and a light detector S, both of which are extended surfaces, rather than differential elements, and which are separated by a medium of refractive index n that is perfectly transparent. Shown. To compute the étendue of the system, one must consider the contribution of each point on the surface of the light sources they cast, raised to each point on the receiver. According to the definition above, the étendue of the light crossing d sigma towards ds is given by dg sigma equals n2 d sigma cos θ sigma dω sigma equals n2 d sigma cos θ sigma dω. s cos theta s d 2. Display style mathroom d g underscore sigma equals n caret 2. Mathroom d sigma cos theta underscore sigma. Mathroom d omega underscore sigma equals n caret 2. Mathroom d sigma cos theta underscore sigma frac mathroom d s cos theta underscore s d caret 2, where d omega sigma is the solid angle defined by area ds at area d sigma. Accordingly, the étendue of the light crossing ds coming from d sigma is given by d g s equals n 2 d s cos theta s d omega s equals n 2 d s cos theta s d sigma cos theta sigma d 2. Display style mathroom d g underscore s equals n caret 2. Mathroom d s cos theta underscore s. Mathroom d omega underscore s equals n caret 2. Mathroom d s cos theta underscore s frac mathroom d sigma cos theta underscore sigma d caret 2. Closing curly bracket, where d omega s is the solid angle defined by area d sigma. These expressions result in d g sigma equals d g s. Display style mathroom d g underscore sigma equals mathroom d g underscore s. Closing curly bracket, showing that étendue is conserved as light propagates in free space. The étendue of the whole system is then g equals sigma s d g. Display style g equals int underscore sigma int underscore s mathroom d g. Closing curly bracket. If both surfaces d sigma and ds are immersed in air or in vacuum, n equals 1, and the expression above for the étendue may be written as d g equals d sigma cos theta sigma d s cos theta s d 2 equals pi d sigma cos theta sigma cos theta s pi d 2 d s equals pi d sigma f d sigma d s. Display style mathroom d g equals mathroom d sigma cos theta underscore sigma frac mathroom d s cos theta underscore s d caret 2 equals pi mathroom d sigma left frac cos theta underscore sigma cos theta underscore s pi d caret 2 mathroom d s right equals pi mathroom d sigma f underscore mathroom d sigma right arrow mathroom d s. Closing curly bracket, where f d sigma ds is the view factor between differential surfaces d sigma and ds. Integration on d sigma and ds results in g equals pi sigma f sigma s, which allows the étendue between two surfaces to be obtained from the view factors between those surfaces, as provided in a list of view factors for specific geometry cases or in several heat transfer textbooks. The conservation of étendue in free space is related to the reciprocity theorem for view factors in refractions and reflections so that the conservation of étendue discussed above applies to the case of light propagation in free space, or more generally, in a medium in which the refractive index is constant. However, étendue is also conserved in refractions and reflections. Figure étendue in refraction shows an infinitesimal surface ds on the xy plane separating two media of refractive indices n sigma and ns. The normal to ds points in the direction of the z-axis. incoming light is confined to a solid angle d omega sigma and reaches ds at an angle theta sigma to its normal. Refracted light is confined to a solid angle d omega s and leaves ds at an angle theta s to its normal. The directions of the incoming and refracted light are contained in a plane making an angle phi to the x-axis, defining these directions in a spherical coordinate system. With these definitions, Snell's law of refraction can be written as n sigma sin theta sigma equals n s sin theta s. Display style n underscore sigma sin theta underscore sigma equals n underscore s sin theta underscore s. Closing curly bracket, and its derivative relative to theta. N sigma cos theta sigma d theta sigma equals n s cos theta s d theta s. Display style n underscore sigma cos theta underscore sigma math room d theta underscore sigma equals n underscore s cos theta underscore s math room d theta underscore s. Closing curly bracket, multiplied by each other result in n sigma 2 cos theta sigma sin theta sigma d theta sigma d phi equals n s 2 cos theta s sin theta s d theta s d phi. Display style n underscore sigma caret 2 cos theta underscore sigma left sin theta underscore sigma math room d theta underscore sigma math room d phi right equals n underscore s caret 2 cos theta underscore s left sin theta underscore s math room d theta underscore s math room d phi right. Closing curly bracket, where both sides of the equation were also multiplied by d phi, which does not change on refraction. This expression can now be written as n sigma 2 cos theta sigma d omega sigma equals n s 2 cos theta s d omega s. Display style n underscore sigma caret 2 cos theta underscore sigma math room d omega underscore sigma equals n underscore s caret 2 cos theta underscore s math room d omega underscore s. Closing curly bracket, and multiplying both sides by ds, we get n sigma 2 d s cos theta sigma d omega sigma equals n s 2 d s cos theta s d omega s. Display style n underscore sigma caret 2 math room d s cos theta underscore sigma math room d omega underscore sigma equals n underscore s caret 2 math room d s cos theta underscore s math room d omega underscore s. That is d g sigma equals d g s. Display style math room d g underscore sigma equals math room d g underscore s. Closing curly bracket, showing that the étendue of the light refracted at ds is conserved. The same result is also valid for the case of a reflection at a surface ds, in which case n sigma equals ns and theta sigma equals theta s. Conservation of basic radiance edit. Radiance of a surface is related to étendue by L e omega equals n 2 phi e g. Display style L underscore math room e omega equals n caret 2 frac partial phi underscore mathroom e partial g closing curly bracket, where n is the refractive index in which that surface is immersed. G is the étendue of the light beam. As the light travels through an ideal optical system, both the étendue and the radiant flux are conserved. Therefore, basic radiance, defined as L E omega equals L E omega n 2 display style L underscore mathroom E omega caret asterisk equals frac L underscore mathroom E omega n caret 2 is also conserved. In real systems, the étendue may increase, for example due to scattering, or the radiant flux may decrease, for example due to absorption, and, therefore, basic radiance may decrease. However, étendue may not decrease and radiant flux may not increase and, therefore, basic radiance may not increase. Étendue is a volume in phase space-Etendue. In the context of Hamiltonian optics, at a point in space, a light ray may be completely defined by a point r equals x, y, z. A unit Euclidean vector v equals cos alpha x, cos alpha y, cos alpha z, indicating its direction and the refractive index n at point r. The optical momentum of the ray at that point is defined by p equals n cos alpha x, cos alpha y, cos alpha z equals p q r. Display style math BF p equals n cos alpha underscore x, cos alpha underscore y, cos alpha underscore z equals p q r closing curly bracket, where p equals n. The geometry of the optical momentum vector is illustrated in figure. Optical momentum in a spherical coordinate system P may be written as P equals n sin theta cos phi sin theta sin phi cos theta. Display style math BF P equals n left sin theta cos var phi sin theta sin var phi cos theta right closing curly bracket, from which d p d q equals p q theta phi d theta d phi equals p theta q phi minus p phi q theta d theta d phi equals n 2 cos theta sin theta d theta d phi equals n 2 cos theta d omega. Display style mathroom dp mathroom dq equals frac partial p q partial theta var phi mathroom d theta mathroom d var phi equals left frac partial p partial theta frac partial q partial var phi frac partial p partial var phi frac partial q partial theta right mathroom d theta mathroom d var phi equals n caret 2 cos theta sin theta mathroom d theta mathroom d var phi equals n caret 2 cos theta mathroom d omega closing curly bracket, and therefore for an infinitesimal area ds equals dx/dy on the xy plane immersed in a medium of refractive index, and the étendue is given by d g equals n 2 d s cos theta d omega equals d x d y d p d q. Display style mathroom d g equals n caret 2 mathroom d s cos theta mathrm d omega equals mathrm dx, mathrm dy, mathrm dp, mathrm dq, closing curly bracket, which is an infinitesimal volume in phase space x, y, p, q. Conservation of étendue in phase space is the equivalent in optics to Liouville's theorem in classical mechanics. Étendue as volume in phase space is commonly used in non-imaging optics. Maximum concentration at it. Consider an infinitesimal surface ds, immersed in a medium of refractive index n crossed by, or emitting, light inside a cone of angle alpha. The étendue of this light is given by d g equals n 2 d s cos theta d omega equals n 2 d s 0 2 pi 0 alpha cos theta sin theta d phi equals pi n 2 d s sin 2 alpha. Display style mathrm d g equals n caret 2 mathrm d s int cos theta, mathrm d omega equals n caret 2 ds int underscore 0 caret 2 pi int underscore 0 caret alpha cos theta sin theta, mathrm d theta, mathrm d bar phi equals pi n caret 2 mathrm d s sin caret 2 alpha, closing curly bracket, noting that n sin alpha is the numerical aperture NA of the beam of light. This can also be expressed as d g equals pi d s n a 2. Display style mathrm d g equals pi mathrm ds mathrm na caret 2, closing curly bracket. Note that d omega is expressed in a spherical coordinate system. Now, if a large surface S is crossed by, or emits, light also confined to a cone of angle alpha, the étendue of the light crossing S is g equals pi n 2 sin 2 alpha d s equals pi n 2 s sin 2 alpha equals pi s n a 2. Display style g equals pi n caret 2 sin caret 2 alpha int mathrm d s equals pi n caret 2 s sin caret 2 alpha equals pi s mathrm na caret 2. Closing curly bracket. The limit on maximum concentration shown is an optic with an entrance aperture S. In air, n equals 1. Collecting light within a solid angle of angle 2 alpha, its acceptance angle, and sending it to a smaller area receiver sigma immersed in a medium of refractive index n, whose points are illuminated within a solid angle of angle 2 beta. From the above expression, the étendue of the incoming light is g I equals pi s sin 2 alpha. Display style g underscore mathrm I equals pi s sin caret 2 alpha, and the étendue of the light reaching the receiver is g r equals pi n 2 sigma sin 2 beta. Display style g underscore mathrm r equals pi n caret 2 sigma sin caret 2 beta. Closing curly bracket. Conservation of étendue g equals gr then gives c equals s sigma equals n 2 sin 2 beta sin 2 alpha. Display style c equals frac s sigma equals n caret 2 frac sin caret 2 beta sin caret 2 alpha. Closing curly bracket, where C is the concentration of the optic. for a given angular aperture alpha of the incoming light. This concentration will be maximum for the maximum value of beta. That is, beta equals pi 2. The maximum possible concentration is then C m a x equals n 2 sin 2 alpha. Display style C underscore mathroom max equals frac n caret 2 sin caret 2 alpha. Closing curly bracket. In the case that the incident index is not unity, we have g I equals pi n I s sin 2 alpha equals g r equals pi n r sigma sin 2 beta. Display style g underscore mathroom I equals pi n underscore mathroom I s sin caret 2 alpha equals g underscore mathroom r equals pi n underscore mathroom r sigma sin caret 2 beta. Closing curly bracket. And so C equals n a r n a I 2. Display style C equals left frac mathroom na underscore mathroom r mathroom na underscore mathroom I right caret 2. Closing curly bracket. And in the best case limit of beta equals pi 2, this becomes C m a x equals n r 2 n a I 2. Display style C underscore mathroom max equals frac n underscore mathroom r caret 2 mathroom na underscore mathroom I caret 2. Closing curly bracket. If the optic were a collimator instead of a concentrator, the light direction is reversed and conservation of étendue gives us the minimum aperture S for a given output full angle 2 alpha. See also edit. Light field. Beam parameter product. Symplectic geometry. Noether's theorem. Beam emittance. References edit. Further reading edit. Grievenkamp. John E. 2004. Field Guide to Geometrical Optics. SPI Field Guides Volume. FG01. SPI. ISBN 0-8194-52947. Zutao Sun et al. 2006. Étendue analysis and measurement of light source with elliptical reflector. Displays. 27. 56–61.